Hello everyone, welcome to lesson 1-3, multiply and divide monomials. Well, quickly here, let's look at this picture that I found online of what a monomial is. A monomial is a one term, okay? So you see here, this is considered a one term, even though we have a number or a coefficient and a variable with an exponent. All of this is one term, because once we identify what the variable is, we can write this down, we can evaluate this and solve for one value. A binomial is one term plus another term. Bi means two, so it's essentially two terms. You see, once you start putting an operation in there, like addition, subtraction, multiplication, division, it becomes more than one. So now we have one term here and another term here. That's binomial. And then trinomials look like this. Okay, this could simply be 5 minus 2 plus 4 without the variables, and it would still be considered a trinomial. And here we have the definition taken directly from our text. A monomial is a number. As you can see, it could just be a number, as you see it right there. A variable, a letter, or a product of a number and one or more variables. It could be a product of a number. A product means what? A number that you get after you multiply it. So here we would get a product once we solve for this, right? You can use the laws of exponents to simplify monomials. So the laws of exponents would mean we would have to replace this variable, or actually the laws of exponent means that if you have the same base, you can work together and simplify the expression with exponents. Okay, let's take a look at this real-world example here. We have arachnids. Spiders in North America can range in size from 1 millimeter in length to 7.6 centimeters in length. That's quite a big difference. Use the table to see how other metric measurements of length are related to the millimeter. Okay, so we have a millimeter, right there. It's 1 millimeter, there's 1,000 of these in a meter, and we write it 10 to the power of 0. 10 to the power of 0 always equals 1, okay? Then a centimeter is 10 of them, right? It's 10 millimeters, so we can write it 10 to the power, or 1 times 10, which is 10 to the power of 1 now, right? 10 to the power of 1 is just simply 10, so that's 10 millimeters there. A decimeter is 100. So it's 10 times 10, which is 10 to the power of 2. And then a meter, okay, 10 times 100, 100 times 10 millimeters, which is 1,000, which would be 10 to the power of 3. Right? Something that can help you visualize is when you see how many zeros you have next to the 1, that'll be your exponent. So here you have 3 zeros, there's your exponent. So a decameter, okay, 10,000 millimeters is 10 to the power of 3, as we had 10 to the power of 3 here, times 10 to the power of 1. You see it? So that would be 10 to the power of 4. We have a hectometer, 10,000 times 10, or 10 to the power of 4 times 10 to the power of 1 is 10 to the power of 5. And finally, a kilometer. 100,000 times 10 to the power of 1 will equal 10 to the power of 6. So that means we have how many zeros? 1, 2, 3, 4, 5, 6. And over here, we have 5 zeros. So it would be 100,000, right? 1, 2, 3, 4, 5. And there it is. Okay, number 1. Look at the entries in the last column, right here. What do you observe about the exponents of the factors and the exponent of the product for each entry? So, of the factors and the exponents, well, what I notice is that the base keeps the same, right? And what are we doing with the exponents? We're simply adding them. So when you multiply bases that are the same, you simply add. You add the exponents. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. 5 plus 1 is 6. So we add the exponents whenever we multiply. When we divide exponential notations with exponents, we subtract the exponent. So when we divide, we subtract exponents. So in short, the exponents are added when the when the base is the same, not the sum. There we go, when the base is the same. Question 2. A megameter is 100 million times 10 or 1 billion times longer than a millimeter. A megameter is 1 billion times bigger than a millimeter. Extend the pattern to write this number using powers. Well, we could simply write 10 to the power of, help me here, 1, 2, 3, 4, 5, 6, 7, 8, 9. To the power of 9. And that right there is a megameter. So what is the key concept? What is the takeaway from this lesson? To multiply powers with the same base, add their exponents. That's simply what we just did. That's what we noticed in the third column. So when we have the same base, 2 here and 2, and we're multiplying, we're simply just going to add the exponents. So 4 plus 3 is 7. So 2 to the power of 7. In algebra, we could see we have a to the power of m and a to the power of n. We don't know what m or n are. We just know that they're different values, but we could add them. We put a to the power of m plus n. And as we said in the beginning of the lesson, a monomial is a number or a variable. A variable just means it's a letter that we don't know the value to. Or a product, we could have 2x, for example. That would be a product of a number and one or more variables. You can use the laws of exponents to simplify monomials. So here we have, here's the law of exponents. When it's the same base, we simply add the exponents. So 3, we have 3 to the power of 2 is here, 3 times 3. Times 3 to the power of 4, 1, 2, 3, 4. Well, we simply add all the 3's together. And how many do we have? 1, 2, 3, 4, 5, 6. 3 to the power of 6. There it is. Notice that the sum of the original exponent is the exponent in the final product. Let's look at these examples together. We have 5 to the power of 2 times 5, and there's no exponent, so it's 5. It's only one of them, so it's 5 to the power of 1, right? You can see that here. 5 squared times 5 to the power of 1. Remember, we're multiplying numbers with the same base, so we add the exponents. And 2 plus 1 is 3, 5 to the power of 3. 5 times 5 times 5 is 125. Now let's try with variables. C to the power of 3 times C to the power of 5. When we add the exponents, we get 8. See, that's C to the power of 8, 3 plus 5. Now we're going to do it with negative and positive monomials. We have negative 3x to the power of 2 times 4x to the power of 5. Simply just work with the base numbers first, following the rules. Negative times positive is always negative. So negative 3 times 4 is negative 12. You can see it right there. Okay, move this up a little bit. And then 2, and it's being multiplied, exponent 2 being multiplied with exponent 5. You add those two, and 2 plus 5 becomes 7. So there it is, negative 12x to the power of 7. Okay, if you think you got it, go ahead and pause the video now and try A, B, and C. And then we'll check it together. Pause now. Okay, I hope you paused and we can check now. Base of 9, 9 to the power of 3 times 9 to the power of 2 is simply 9 to the power of 5. One step that I did not put in there is simply doing this 9 to the power of 3 plus 2, correct? 3 plus 2, and then it would give me 9 to the power of 5. With B, we'll have the variables. A to the power of 3 times a to the power of 2 is the same thing as writing a to the power of 3 plus 2, which equals a to the power of 5. And we have a negative monomial times a negative monomial. Negative 2m times negative 8m to the power of 5. How many m's do I have here? Only one. So this is actually to the power of 1, isn't it? And this is to the power of 5. So we could rewrite it like this if we wanted to. Negative 2m to the power of 1 times negative 8m to the power of 5, right? So don't forget, when they don't write an exponent, but there is a variable, there's one of them right there. Okay, so don't forget there's one. So negative 2 times negative a equals positive 16. M, so now I have to add this 1 plus our 5. 1 plus our 5 equals 6. And there's your answer. 16m to the power of 6. And here's the other part of our lesson. So as I mentioned earlier, to divide powers with the same base, subtract their exponents. So if you have the same base, you subtract the exponents instead of adding them. When dividing, you subtract exponents. When multiplying, you add exponents. So here's an example. We have 3 to the power of 7 divided by 3 to the power of 3. You take your same base and you subtract the exponents and you get 3 to the power of 4. When you do it with algebra, you have just your variables am divided by an. Now these are not the same variables, which means they cannot subtract one another until we actually understand what m is and what n is. So we simply write it as a to the power of m minus n. This is us making a note of what needs to happen once we understand what m and n are. So where a cannot equal 0, because if a equals 0, everything equals 0. There's also a law of exponent for dividing powers with the same base. So the law of exponents, so you have 5 to the power of 7 divided by 5 to the power of 4. So we're essentially going to write our 5, all 7 of our 5, because it's 5 repeated 7 times, right? And then we write it here, repeated all at the same time. So we're dividing 5 divided by 5. Gets rid of it. 5 divided by 5, 5 divided by 5, and 5 divided by 5. Those cancel each other out, leaving us with only these 3. So those 4 factors are gone, so it's 5 to the power of 3. There, that's all that we have. Notice that the difference of the original exponents is the exponent in the final quotient. So the difference between these two exponents is our actual quotient. The difference between 7 and 4 is 3. So as we saw in the lesson just above, we will see here in these examples. So you see 4 to the power of 8 divided by 4 to the power of 2. We simply subtract our exponents and we get 4 to the power of 6. With the variable n to the power of 9 divided by n to the power of 4, we simply subtract the exponents and we get n to the power of 5, because 9 minus 4 is 5. And then we can do it with multiple numbers at the same time. As long as the base is the same, we can work with them. You see these bases are the same, these are the same base, and these are the same base. 2, 2, 3, 3, 5, 5. So we just simply subtract down. Okay, 5 minus 2. Okay, 5 minus 2 is 3. You see it right there. 5 minus 4 is 1. So it's 3 to the power of 1. You don't even have to write 3 to the power of 1. You can just simply write 3. And 5 minus 1, because it's 5 to the power of 1. You just don't write the 1. Okay, you see that? It's going to be 5 to the power of 1, but again, you don't write the 1 there. So it's 8. If you wanted to write it in standard notation, 2 times 2 times 2 is 8, times 3 times 5, which is 120. Sometimes you will not get them in that nicely arranged order with 2 is above 2 and the 3 is above 3 and the 5 is above 5. No, sometimes you get them mixed around. So you'll have to use commutative property to move them around so they can align with the ones that you want to subtract. So group by common base, as I just mentioned. You group them by the common base, then you subtract the exponents, and then you solve. You write them in standard notation, not exponential notation, standard notation, and then you evaluate, you simplify it to 120. Okay, here's D to I. If you feel ready for this challenge, go ahead, pause the video, and try these all on your own, and then play the video again when you'd like to see the answers. Pause now. Okay, let's see D. Same base is 5, so it's 7 minus 4 is 5 to the power of 3, right? You could show your work by putting the 4 there and showing that you're subtracting the exponents too. E. Now we have a variable. X to the power of 10 minus x to the power of 3. Okay, and again, you could show your work by writing x to the power of 10 minus 3 equals x to the power of 7. Now we do not have the same base right here, but we do have the same variable. So these could work. But for the same base, we have 12 divided by 2 is 6 12 divided by 2 is 6. And w to the power of 5 minus w to the power of 1 is w to the power of 4. Do you see how this is 1? I just wrote it in, but there's only one w. For d, they grouped them for us very nicely. So we'd simply just have to solve by doing 3 to the power of 2, 3 to the power of 2, where I subtracted here, and now I have 5 to the power of 2 minus 5 to the power of 1. Okay, there's only one 5, and it becomes 5 to the power of 1. 2 minus 1 is 1. So I just write my 5. Okay, essentially we're getting rid of that. And then 7 to the power of 5 minus 7 to the power of 3 equals 7 to the power of 2. Again, they're nicely grouped for us. 5 to the power of 6 minus 5 to the power of 4 is 5 squared, 5 to the power of 2. 7 to the power of 4 minus 7 to the power, or divided by 7 to the power of 2, I should say, is 7 squared. And 8 to the power of 3 divided by 8 to the power of 2 is simply 8, because 3 minus 2 is 1, and I don't need to write the 1 there. I'll just write it as is. If we wanted to solve, simplify, evaluate completely, then now we have 5 to the power of 2 is 25 times 49, because 7 times 7, times 8. And then you can solve for that by multiplying all three numbers together, and you would get 9,800. I think, yes. Now we have them grouped again, right, where it's the same base, so I can just simply subtract. So negative 2 to the power of 5 divided by negative 2 to the power of 2 is going to be negative 2 to the power of 3. Right? I'll keep it in parentheses the way they have it. And then times 3 to the power of 4 divided by 3 to the power of 1 is going to be times 3 to the power of 3. And then with the same base, we have 5 to the power of 7 divided by 5 to the power of 4 is 5 to the power of 3. Or, if we wanted to solve for this, we would simply solve here by multiplying negative 2 times negative 2 times negative 2, okay, which you guys already know. It's going to be a negative number. It's going to be negative 2 times negative 2 is positive 4 times negative 2 is negative 8. And then 3 times 3 is 9 times 3 is 27. And then 5 times 5 is 25 times 5 is 125. Yeah? And then when you solve for that, you should get negative 27,000. And finally, a real world example. Hawaii's total shoreline is about 2 to the 10th power miles long. New Hampshire shoreline is about 2 to the 7th power miles long. About how many times longer? It looks like we're looking for a difference, right? Is Hawaii's shoreline than New Hampshire's? To find how many times longer, divide. We're looking for the difference, right? So we're going to divide how many of these are in this. And the difference in terms of exponents, because we're saying how many times bigger, how many more, to the power. So we're going to divide 2 to the power of 10 divided by 2 to the power of 7. We get 2 to the power of 3. So Hawaii's shoreline is about 2 to the power of 3, or 8 times longer. Here's your guided practice for class. This is how we will begin class. Please take a look at the examples 1 to 6. If you are not sure on how to do any of these, go back to the video, examples 1 to 6. And if you're not sure on how to do the word problem, take a look at example 7 just above. Okay, there's the graph. Do you need French and Sicilian for the languages? Okay, everybody, see you in class.